My computer is actually out of space, so I just need to submit. Just one second. Okay, so this one. We'll just try to quickly. I'll share the notes with you. We'll just try to quickly go through all the organic chemistry that's available. And so starting with the first thing, and most of the initial stuff is just basic revision of what you've already done in AS. So what it's all about is you need to know all the formulas, the molecular formula, the structural formulas, which atom makes how many bonds. The structural formula is going to have many versions. It's going to have the fully displayed formula where you show all the atoms and bonds. Then you're going to have the condensed formula where you can just condense the structure if you just travel from left to right. For example, this is CH3, this is CH. With the CH3 branch, you put that in brackets. Then you've got C. With an OH branch, you put the OH in bracket. With another CH3 branch, you put that in bracket, and then COOH. So condensed formulas, make sure you know how to write distillate formulas as well as condensed formulas. And then there were skeletal formulas where what you did was that you would just draw the carbon atoms, and even they would be represented by dots. So you had 4 carbon atoms. So 4 carbon atoms, that's 1, 2, 3, 4 carbon atoms in a line. Okay, so that's your 4 carbon atoms. That's 1, 2, 3, and 4. And then you had 4 carbon atoms in a straight line, and then you had a carbon atom that was on the second one, another carbon atom on the third one. You had an OH on the third one. So you drew the functional groups, but did not draw the carbon atoms. They were just represented by dots. So they were skeletal formulas. So you need to know how skeletal formulas are formed. You need to know some basic naming, which you've already covered in AS, and that's the number of carbon atoms. That's 4, so that's bute. Carboxylic acid, so it's oic acid. The middle part is AN or EN, depending whether it's saturated or unsaturated. So this one, if you have a double bond, it would become EN. You have to give the positions of the functional groups of all the groups that are present. So the double bond is at carbon number 2, and the carboxylic acid is at carbon number 1, which it always is at carbon number 1. You've got butanone, which is 4 carbon atoms. It's a ketone, so you need to know how many functional groups you've got. So remember, you've got alkanes. So you've got alkanes, alcohols, carboxylic acid, nitriles. You've got aldehydes, and you've got ketones. So all these functional groups are you need to know the basic naming mechanism of how to name these compounds. Here we started organic TK for quick revision. Maybe we'll do past refers in the middle part. Just 1 second. I said then the next thing is okay, we've got 1 second. As the next thing is so basic level naming. Counting is done from the side that has the higher precedence group. So you always give importance when you're numbering the carbons, and you always give importance to the group that has a higher precedence. For example, the carboxylic acid has a higher precedence compared to all of them: nitriles, aldehydes, ketones, alcohols, amines. You don't need to go into a lot of detail. For example, this one, we can skip this one just 1 second. Do the easy ones first. So if you have a molecule, you look for the longest chain, longest carbon atom chain that has the maximum substituent groups, maximum functional groups attached to it. and it should also have the highest precedence group. It should be part of the main chain. So whenever you're given a molecule, you look for the longest chain, which in this case is this one. This one has the most number of groups attached to it. It's the longest continuous carbon atom chain. It's got an aldehyde, it's got an alcohol, it's got carbon chains, which are methyl chains, methyl groups attached to it. So it's got all the maximum groups attached to it. So you're going to start with the main chain. You're going to start with naming the main chain, which is if you've got the longest chain in this case is 1, 2, 3, 4, 5, and 6. So that's X. And it's unsaturated, so it's EN. It's an aldehyde, the highest precedence group over here. That's an aldehyde. So you're going to call it an aldehyde. And then you're going to number it based on the aldehyde. You have to give the smaller number to the highest precedence group. So you start off with this one is going to be 1, this is 2, this is 3. So the alkene is going to be at number 3. So it's going to be called hexenal, and it's going to be the alkene is going to be at position number 3. And then you're going to put in all the branches. There's a hydroxy branch, there's a methyl branch, 2 methyl branch. So there's a dimethyl branch, there's a hydroxy branch. The hydroxy branch is at position number 5. And your methyl branches are at positions 2 and 4. Now, and that's the skeletal formula for the same one. But anyways, still AST. So you need to know about structural isomers. Structural isomers are of 3 types. Structural isomers are when you rearrange the atoms in a different way. So the first one is chain or branch isomers, where you change, what you do is you change the carbon branches. That's your chain isomer. Positional isomers are where you change the position of a certain group. Functional group isomers are when you change the functional group altogether. So isomers are same molecular formula, different structural formulas, and in functional group isomers, aldehyde and ketones tend to be isomers of each other. Carboxylic acid and esters, they tend to be isomers of each other. You've got alkenes and cycloalkanes, they also tend to be isomers of each other. And you've got another type of isomers which you studied in AS, and they were stereoisomers. So they had the same molecular formula, they also had the same exact structural formula as well. Now, in stereoisomers, you had two different subsets. One was geometric isomers, known as cis trans. The conditions for that is you needed double bonds and you needed both groups to be different on both sides of the double bonds. So this carbon must be bonded to 2 different groups. This carbon must be bonded to 2 different groups as well. The rotation would get restricted because of the double bonds, which is why the molecule would have 2 shapes, 3-dimensional shapes. Either the CLs would be pointing downwards or the CLs would be pointing in opposite directions. So you had cis and trans isomers, which I'm pretty sure you already know of. So we can skip to optical isomers quickly. In optical isomers, you had, that was the other version. In optical isomers, you had enantiomers. You had a carbon atom, which was chiral, which was bonded to 4 different groups. And it had 2 non-superimposable mirrored versions of each other. And any carbon that's bonded to 4 different groups, that's going to be chiral. And enantiomers are differentiated because they rotate plane polarized monochromatic lighting. They all have very similar properties, physical and chemical properties, but they will rotate plane polarized monochromatic lighting in opposite directions. So that was optical isomers. And you did this in AST. There were lots of questions where you'd be asked to find out chiral centers, how many chiral centers it's going to have. So you would look for carbon atoms that would have 4 different groups attached to them. So starting with alkanes, again, still revision. Alkanes, you can read these notes on your own about the revision part. I'll just focus on A2 right now. So alkanes were saturated molecules. They were making single bonds. The carbon was sp3 hybridized. In AS, you only did one reaction for alkanes, and that single reaction for alkanes was called free radical substitution, where what happened was the free radical substitution was not alkane specific, by the way, it was a carbon chain specific reaction. That if you had a carbon chain and a bunch of hydrogens, then any of those hydrogens could be substituted by Cl, or they could be substituted by Br, depending on what the reagent is. UV light was necessary. The reaction would not happen with fluorine or iodine. UV light was necessary, and any of the hydrogens would get substituted. So it could be multiple Cls coming in, or maybe just one Cl at any specific position, but it would happen in the carbon chain. And in A2, you get this reaction very often because there are other reactions where there's a reaction with chlorine. But remember, with UV light, you always get a substitution happening in the alkyl chain or the carbon chain. You had mechanisms for free radical substitution, which probably is not going to be asked in A2, but just a quick recap, that you had chlorine, it would form free radicals. Free radicals were species that had unpaired electrons, or they did not have complete, the bonding was not complete, or the outer shells were not complete. They had an odd number of electrons. So the chlorine molecule would break down under UV light, and it would produce two Cl radicals. The Cl radicals would then go and steal hydrogens from the carbon chain. And they would form HCl. So the carbons would be left without hydrogen atoms. So the carbon would become a radical, and the carbon would go and then steal chlorine from chlorine molecules, and a chlorine would bind with the carbon atom. Another Cl radical would get produced. And the same thing continues. The Cl radical would then go along and then steal any other hydrogen from the carbon chain, and it would become a radical. And the propagation would just continue. The carbon would then steal one of the chlorine from the chlorine molecules and bind with that chlorine, so there would be substitution happening, and more Cl radicals would get produced. And there was this other step which was called, this one was called the termination step, that at any point the reaction could terminate, that any of the free radicals could simply just combine with each other. If there are free radicals being produced, they're just short of bonds. So why don't they just bond with each other? If they bond with each other, no new free radicals are going to be produced, and that would terminate the reaction, because without free radicals, the reaction will not continue. So this was the mechanism for free radical substitution, that free radicals got produced. The free radicals then stole the hydrogen atoms, formed HCl. The carbon became radicals then in the carbon chain. They started stealing Cl atoms from Cl molecules. Substitution started happening. So basically, just remember that UV light, any of the carbon chain that could be substituted, and it could form a substitution product. I said this is about crude oil, that's kind of 4 levels. Now this is now very similar to what you're going to study in A2. So quick recap for this is that you've got alkenes. And what alkenes do is that, what alkenes do is that they're sp2 hybridized, and carbon had 4 electrons. So out of those 4 electrons, carbon ended up making 3 bonds, not 4. And there was a 4th electron that was left. So there was a 4th electron that was left in sp orbit. And that 4th electron would go on and it would form a pi bond. And there would be electron densities, there would be a double bond. There would be a sigma bond, the carbon would share 1 electron in the middle. Carbon would share an electron with hydrogen, carbon would share an electron with another hydrogen atom, so it would form 3 bonds. But the 4th electron, they would overlap above and below. And when they overlap, this electron cloud has a very high electron charge density. So, so the alkene double bond is going to be it's going to be very, very reactive. It attracts electrophiles. Electrophiles are species that are attracted to electrons. So it attracts electrophiles very, very strongly. So remember this part, that alkenes have an electron cloud that has a very high charge density, which is why it has electrophilic reactions, which are very, very vigorous. So a benzene molecule was something that was very similar to what an alkene is. You can think of a benzene, and remember, they're going to ask you for the structure of benzene very often. So benzene is kind of something that's very similar to an alkene, that it also has a double bond. Now, what happens in benzene, and this I've written that don't use this structure, they use a different structure, but this one is a structure that is more easier understandable. So what happens is that carbon in a hexagonal ring structure is making three double bonds, alternating double bonds. And since carbon is making a double bond, it is sp2 hybridized. So all carbon atoms in benzene are sp2 hybridized. The carbon-hydrogen ratio is 1:1 if this is C6H6. One way to identify a benzene in the formula is when you have a very low carbon-hydrogen ratio, that kind of indicates that it's a benzene. Now, this is what happens in benzene, that the carbon is making three bonds, just like an alkene, and there's a fourth electron, a p orbital, which is not doing anything. That carbon is also making three bonds, and there's a fourth electron that is initially not doing anything. And all these carbon atoms are exactly identical. They're all sp2 hybridized. Now, what happens is that normally a pi bond is formed when two p orbitals they overlap. So if you look at the blue ones, you can appreciate them. So the blue orbitals might overlap, and they would form they're going to form a pi bond. And they would overlap above and below, and that's how normally pi bonds are formed. A pi bond could be formed over here, a pi bond so a pi bond is getting formed over here. But instead of forming three pi bonds or three double bonds, what eventually happens is that the pi bonds, they get delocalized. What eventually happens is that all six of them, they eventually mix up and they overlap, and the p orbital over here, the one that is shaded, not only overlaps with the p orbital on the left side, it also overlaps with the p orbital on the right side. And what you eventually have is not three double bonds in three different positions. What you eventually happen is you've got a ring structure, which is you just have a pi electron cloud that's all over the place. So that's what benzene is, and that's why it's different from an alkene. That it doesn't have the same type of pi bonds. The pi bond charge density is going to be a lot lower. Why would it be lower? Because the electrons are not only overlapping on the left side, they're also overlapping on the right side. So the electron charge density kind of decreases. And since it decreases, there's too much overlapping happening. So the electrons are kind of more spread out. So the charge density is a lot lower. So electron density in a pi electron cloud is significantly lower compared to an alkene pi electron cloud. Which is also, if you look at the bond strength, it also is reflected in the bond strength. That you've got a single bond, you've got a double bond, that's a pi bond. And the benzene is kind of somewhere in the middle. So this thing over here is kind of something that's in between a single bond and a double bond. It is not exactly a double bond, because in a double bond, the electrons are in one place. Over here, the electrons are distributed on both sides. So the charge density is significantly lower. And which is why the alkene pi electron cloud does not attract electrophiles very strongly. So alkene pi electron cloud charge density was significantly higher because the electrons were in one place. All the electrons were exactly in this middle part over here, which is why the charge density was significantly higher. But in benzene, it's significantly lower. So it does not have the same reactions as an alkene. You'll be asked to describe the structure. So what you're going to write about this structure is that you have to, you get a 5 to 6 mark question asking for a description of the structure. So just remember that that carbons are all sp2 hybridized. The bond angles are all hexagonal planar structure. It's all 120 degrees. The carbon-carbon bond, that's a sigma bond, that's an sp2 overlap. The carbon and hydrogen, they also form sigma bonds. I mean, carbon and hydrogen on the outside. And that's an sp2 overlapping with an s orbital of hydrogen. And you've got pi bonds, which are p and p overlapping with each other. And they end up forming a ring of delocalized pi electrons. Now, so remember this difference. I say clear difference is this. But clear, yes or no?
Yes, sir.
I say I'm moving. I said I'm moving on. As I'm moving on, so alkenes have significantly higher charge. Have you seen it? Can you hear it properly? So alkenes have significantly faster reactions. Again, this is going to be asked a lot in A2. So remember electrophilic addition, although that's part of AS. Alkene, the electron cloud is very localized. It's at one position, which is why it's got a very high charge density. The pi bond strongly polarizes the bromine molecule. So what it does is it polarizes or repels the bromine electrons, and you get a very positive bromine, you got a very negative bromine. The positive bromine goes and grabs the electron cloud, bonds with the carbon atom. The other carbon atom becomes a carbocation, then the Br- one goes and bonds with the other one. And that's electrophilic addition. So that's the mechanism that's written over here. You get carbocation intermediates in this. The carbocation intermediate is formed. It's a two-step reaction. Now that's electrophilic addition. So you've got 4 electrophilic addition reactions which are kind of similar. One is bromination. You need to know that. That's AS again. You've got Br2 aqueous or Br2 in an inert solvent. You get bromination. Bromines get added to the double bond. You've got hydration. Water gets added to the double bond. H and OH, phosphoric acid, 60 atmospheric pressure, and 300 degrees centigrade is the catalyst. And then you've got nickel and platinum catalyst, which is 152, 200 centigrade, and the hydrogen molecules they get added to the double bond. Now, and there's one more which is hydrogen halides with hydrogen halides HCl and HBr. At room temperature, H and Br are going to get added to this. Now, the thing is, some more stuff about mechanism. There used to be a Markovnikov's rule, which was about carbocation stability, which basically meant that the Markovnikov's rule was that if you had an unsymmetric alkene and you had an addition reaction, the HBr would get added to the double bond. Now there were two options. The H could get added to the carbon on the right side, and that would give you this molecule over here. Or the HBr molecule could get added to the H could get added to the carbon on the left side, and the Br could get added on the right side. So there were two options that could have happened. Now the rule was for unsymmetric alkenes, the rule was that the H likes to get bonded to the carbon that's in the serial bond C, which is already bonded to more H atoms. So one of your product was a major product. So this one was your major product, which meant that the H likes to bond with the carbon that's already bonded to more H's. This one is bonded to more H's. There are two of them. While this one is, the left one is not bonded to, it's only bonded to one H directly. So you've got a major product and you've got a minor product. And it all depended on the stability of the carbocation during the mechanism of the reaction. The mechanism of the reaction was this: that when HBr molecule was bonding, the positive H from the HBr would try to attract the electrons from the triple bond, right? Now that H could bond with the carbon on the left side. So you're going to get either this carbocation, or it could bond with the carbon that's on the right side. So you're going to get this carbocation. Let me make a circle around. So you add this H that was coming in. And that H could bond with the carbon on the left side of the double bond or on the right side of the double bond, and you will get carbocations. The Br minus one would then come in and bond with the other carbon. Now, one would result in a 1 degree carbocation, the other one was a 2 degree or a secondary carbocation. A 1 degree carbocation is one usually at the end of the chain, where the carbon positive is at the end of the chain, and it's got just one carbon chain attached to it. So if you're standing over here, there's only one carbon chain that's attached on the left side. A 2 degree carbocation, like if you stand on that 2 degree carbocation, you will see two carbon chains attached to it. There's a carbon chain on the right side, and there's a carbon chain that's on the left side. So the idea was that 2 degree carbocations, they tend to be more stable, or they're more easily formed. And the reason for that is, or higher degree carbocations are more stable. Now, the simple reason for that was, and remember in A2, they're going to ask you about this as well, about carbocation stability. So carbocations that have more electron donating alkyl chains are more stable. So the ones that are more surrounded by carbon chains, like a 3 degree carbocation is surrounded by carbon chains on all sides. A 2 degree carbocation is surrounded by carbon chains on two sides. A 1 degree carbocation has only a carbon chain on the left side. So when you're surrounded by carbon chains, there are too many electrons around you, which makes the positive charge on the carbon very, very small. So it is easier to form. It's always easier to form something that has a very small positive charge. And it's going to be very stable as well. It's always more difficult to actually form something that's got a very big positive charge, because this carbon over here, it's got very few electrons around it. So the positive charge is not going to be neutralized to a very large extent, and it's going to be a very big positive charge. So something that's got a big positive charge, that's very hard to form, because somebody would have to steal electrons from it. So if it has a very big positive charge, it would be very hard. I mean, why do you form a positive charge? Because somebody stole electrons from you. So if you've got a very large positive charge, then no one would actually be able to steal electrons from you, because you'll be able to actually pull those electrons back. So the idea is that if your carbocation, like the H was the one that came in from HBr and stole electrons from the molecule. So if the positive charge in a 1 degree carbocation is big, then the H will never be able to do that. It won't be able to steal electrons from it. If the positive charge is small, then the H will be able to steal electrons from it. So the idea is that that carbocations that have a very low charge density, like a 2 degree or a 3 degree carbocations that are much more easier to form, because anyone can steal electrons from it, the H can steal electrons from it, and it will not attract those electrons back because the positive charge is kind of weak and small. If it's large, then the H will not be able to steal electrons from it in the first place, and the positive carbocation will not be formed. So is this idea clear that carbocations with more electron-donating alkyl chains, that they are easy to form? Is this clear?
Yes, sir.
So moving on. Now let's start with, so that was alkenes, that was electrophilic. Addition of alkenes. Now we're going to move to benzene. Remember, benzene is kind of similar. It's got an electron cloud, and think of that as a pi-electron cloud, but remember it's more distributed. So it's like 3 double bonds that have all gotten mixed up. So initially, the first one, electrophilic substitution in benzene. There are 3 electrophilic substitution reactions mainly. You've got a bromination reaction, where you've got an FeBr3 catalyst is required. The reaction, so this is the first one, is bromination. You've got chlorination as well, where you have an AlCl3 catalyst. And you've got a nitration reaction, where what happens is that you've got in a nitration reaction, what happens is you need concentrated nitric acid, sulfuric acid, and the temperature is going to be 55. In all 3 cases. In the first one, remember benzene had all these 8 atoms. So the reaction is simple. Bromines will get added, chlorines will get added, or NO2 is going to get added to benzene. So that's electrophilic substitution, just like electrophilic addition, where things get added to the double bond. Here, bromine, chlorine, and NO2 get added to the benzene. But the mechanism is quite different. So the mechanism is that you've got a benzene with its electron cloud all over the place. I mean, it started off with 3 double bonds, but all of them, they got mixed up. So you've got a benzene, the electron cloud density is very low, unlike an alkene. So the polarization of the bromine molecule is going to be extremely weak. It's not going to be very polarized. The benzene will try to push electrons of bromine away. It's going to repel them, but the repulsion is not going to be large. It's going to be weak. One of the bromine will be slightly negative, the other bromine will be slightly positive, but the polarization is not strong enough. The positive charge is not very large, which is why it's not that attracted to the electrons over here. So what you do is, you need a catalyst for that. You need FeBr3 catalyst. The Fe pulls the electrons from the other side. So that is what increases the polarization. So the catalyst is very necessary so that the bromine molecule could be polarized. And then what you have is you've got a positive bromine. The positive bromine then gets attracted to the benzene, steals one of the electrons from the pi-electron cloud, and bonds with the carbon atom. The electron cloud is electron deficient. It gets a positive charge because the bromine over here, this bromine over here, came and stole one of the electrons from the carbon atom. The other Br-1 went and got itself attached to the Fe over here, and it ended up forming a double bond. So that's your intermediate. That's your benzene intermediate. And then what you do is what happens after that is that the benzene electron cloud is very unstable because it is short of 1 electron. So what then happens is that the H, which is kind of electropositive, loses the electrons, gives the electron back to the benzene electron cloud, and the benzene electron cloud becomes complete again. So the H leaves, leaving the electrons behind. And where does the H go? The H goes and bonds with the bromine which had earlier broken off, and they form HBr. So that's your mechanism for electrophilic substitution. And remember, unlike alkenes, the difference is now you've got substitution, you don't have addition. So the difference is that that the bromine is harder to polarize, so the reaction needs a catalyst. You can't do the reaction without a catalyst. And the second thing is that you get substitution. The reason you get substitution is that the benzene electron cloud is very stable. It's got a very low charge density. So it's easier to form. So which is why the electron cloud reforms. Unlike in alkenes, the electron cloud never reforms. Once the electron cloud is gone, it's gone. The molecule in alkene becomes saturated. Over here, the electron cloud comes back because firstly, the electron cloud is so large that it's very hard to actually get rid of the whole electron cloud. And secondly, just for stabilization of the electron cloud, because it's missing one electron, the electron cloud reforms back again. When the H is the one that ends up leaving electrons. So this is your exam mechanism, and they're going to ask you a lot about this. And that's electrophilic substitution of benzene. Bromine molecule gets polarized. Positive bromine goes and bonds with the carbon. The electron cloud becomes partial. DH then gives its electrons back, and the electron cloud becomes completely. So we're going to continue with this, and we're going to try and finish electrophilic substitution in the next class, and then we'll do some past papers related to this. Okay? And I'll share these notes in the group as well. Okay, everyone.